Hi everyone! I would like to welcome you all to this presentation about the applications of FT and IR technology at the sugar mill industry. I would like to thank you, Nicholas from Solar Datalab, for the invitation and also for setting up this meeting. I will start here making some presentations, starting with me. I am Ana Peinado. I work since 2014 as a technical and sales specialist at Bruker do Brasil, at the optics division, especially for the chemical, pharmaceutical, and sugar and biofuels market. The applications I will share with you today regards to some of my experience within Brazilian sugar market, mills, and quality control standards. Following with the presentations, Bruker Optics is the division of Bruker Corporation that offers analytical solutions in molecular spectroscopy for the most varied applications, from research, development, quality control, and also process control. For molecular spectroscopy, we can understand the techniques that use the infrared or near or mid-infrared or Raman techniques for analytical purposes. Before we go into the possibilities of applying NIR analyzers in the sugar industry, I'm going to make a brief introduction about the analytical technique itself. So what is exactly NIR or NIR in spectroscopy? The spectroscopy itself is an optical analytical method based on the study of the interaction of light with the matter. In this study, a beam of light of a certain wavelength is focused on a sample that will absorb part of this energy and transmit or reflect that part that wasn't absorbed. Usually, the relationship between energy absorption and analyte amount are proportional. The radiation frequency used in NIR spectroscopy is in the infrared region, comprised between the visible light and the microwaves in the electromagnetic spectrum. This type of interaction with NIR causes vibrations in some types of bonds between molecules. The NIR or near-infrared technique has its names because it considers the region closer or near to the visible spectrum between 800 and 2500 nanometers. Each type of chemical bond absorbs IR energy at a specific wavelength, and as a result of those interactions, we have what we call the NIR or the MIR spectrum. The infrared region is divided into smaller parts, each one with specific properties. MIR spectra are formed by the fundamental vibrations of the molecules and have the characteristic of being like the fingerprint of molecules or the samples, and are mainly indicated for qualitative analysis or identification or verification purposes. On the other hand, NIR spectra are composed by vibrational combination bands and overtones, signals that have lower intensity. Those lower intensity enables the quantitative analysis of various types of products as they are, without complex sample preparations. The main types of bonds that interact with the infrared are those mentioned below: CH, OH, and NH, mainly organic molecules. As they are secondary analytical techniques, the infrared applications depends on the development of databases for comparison or calibration models. For quantitative models, for example, the spectra of a set of samples that represent the analysis routine and their respective values analyzed by the primary methods are needed. With those data, predictions models are generated using, for example, the PLS mathematical algorithm. The infrared spectroscopy brings some relevant advantages for the more complex analysis, or those carried out in large quantities, because normally the analysis is carried out without any sample preparation, which allows the automation of this analysis and reduces systematic errors. In addition, it's a fast analysis, usually done in seconds, and can present a variety of sample information in a single reading. It also has the flexibility to analyze products in multiple presentations. The operation is very simple and intuitive, and transfer of methods between devices is uncomplicated. As it does not require sample preparations or reagents or solvents, the cost per analysis is practically zero. Now let's start talking about the possibilities of NIR analyzers in the sugar and alcohol processes. Keeping in mind that as only some specific groups of chemical bonds interact with the IR, the applications stand out mainly with the investigation of organic compounds or moisture. Some of the determinations like inorganic properties or at very low concentrations cannot be handled by NIR or MIR. The application opportunities are found in the main process stages at the mill, starting with the recipe of sugarcane, with analysis to determine the sucrose content, for example, like for payment or pre-harvesting analysis proposals. Following the process, we will talk about the applications at the milling and juice extraction steps, also applications in production and refining of sugar, and finally the process of fermentation and distillation of ethanol. Let's start with the incoming raw material. The analysis of shredded cane in incoming lab generates essential data for both process mass balance and payment of suppliers. The wet chemical analytical procedures for determination of sugar content include several and exhausting steps, as the amount of samples to be analyzed in the routine is usually very high. The determination of main properties from a shredded cane sample with FTNIR MPA2 is very simple and easy. Once homogenized, the sample is disposed at the extra-large sample cup and the spectra is measured. The calibration models developed previously will predict those cane properties within a minute. The sample cup bottom is made of quartz and can be easily cleaned and prepared to the next sample. In addition, as MPA2 is a multi-channel analyzer, it can also analyze liquid samples as juices. Whether automation is a target, NIR can also be used. The use of Matrix F CPS system equipped with an emission sensor and a conveyor sampling system can automate a large part of the operation, considerably increasing the availability to analyze the greater number of samples. In this application, the NIR sensor is coupled to a sampling system that will transport the shredded cane from the disintegrator up to the sensor. Here in this video, we can see how the shredded cane is transported on the belt until it is measured by the NIR sensor. At the end of the sample reading by the NIR sensor, bricks, pole, and fiber results are automatically generated, predicted through the dedicated calibration models, and this information can also be followed to a data management system such as PIMS. Following to the next process step, we have the mills. Controlling the variables at the milling process is vital to optimizing extraction yield and efficiency. As with the receipt of sugarcane, the shredded cane can be analyzed directly in the real-time process using emission sensors. Not least, the emission sensors can also be used to monitor the control properties on the bags directly at the belt, determining the residual sugar and moisture in this material before it is sent to be burned at the boilers for energy production. The typical performance of calibration models for these three products presents high correlations and standard errors very similar to the ones provided by the QC lab. For these applications, Matrix F is the best choice. As in a single analytical system, it can combine sensors for reading solid samples and probes for analyzing the liquids. For example, using a single analyzer, it's possible to monitor three different measurement positions, like shredded cane, juices, and bags. The analyzer itself allows up to 6 measurement points, and these points can be installed up to 125 meters away from the analyzer, as the sensor or probes are connected to the spectrometer through fiber optic cables. For the installation of the emission sensor, Bruker offers this type of adapter to be attached to the side of the mill. The optical interface is a highly resistant and robust sapphire window. Here I have some pictures of this type of sensor installed at the mill. In this type of installation, only the sensor is located inside the process area, while the analyzer itself can be accommodated in a safer location. As they are part of the analytical system, if you have a problem with the sensor, only this part should be replaced for maintenance, not the entire analytical system, so you can reduce downtime of the system whether you have some problem. For the application in juices, Bruker uses immersion probes that can be installed in pipes, for example, and are constantly monitoring the properties of the product, such as bricks and pulp contents. At the sugar production stage, several intermediate byproducts are analyzed at the QC lab for process control. These byproducts, as syrups and magma, can be easily and rapidly analyzed to determine the bricks and pulp content, both with a single sampling and measurements. This brings agility and improves the process control with fast and accurate information. Still inside the QC lab, not only the byproducts can be easily analyzed, but also sugar products. Both raw or white sugars can be specified quickly and effortless. Quality parameters such as pulp, ashes, moisture, and color can be delivered within 60 seconds using Bruker calibration starter spec. At the QC lab, Tango R is a comprehensive solution and can handle liquids, solid, and paste samples. Tango comes with the right accessories to provide the best sampling technique for different types of products. Whether you use Bruker starter spec or develop your own models, the instrument can generate up to 10 results with a single sampling reading. Tango is a compact, intuitive, easy to operate instrument, and as the other FT&IR instruments from Bruker, it's built with the high technology rock-solid interferometer, with its permanently aligned cubic corner mirrors, turning into a reliable and robust solution. Regarding the application in sugar, the same emission sensor can be used to monitor the quality parameters at the process as well. Without contact with the sample and directly over the conveyor belt, Matrix F with emission sensors can be monitoring in real time the quality parameters of sugar and integrate these results with the control room. Finally, we are into the fermentation and distillation process. In both stages, online FT&IR technology is an option that provides good opportunities for real-time process control and optimizing throughput and processing times. How would it be if you can have real-time data from the fermentation process, monitoring every minute the consumption of sugars and the yeast activity? In the fermentation stage, it's possible to use probes installed directly in the fermentation tanks to monitor this consumption of sugars, the production of ethanol by the yeasts, and some fermentation byproducts such as organic acids in real time. Here too, an advantage of Matrix F system is that you can monitor multiple tanks with a single multiplexed analyzer and several immersion probes. Similarly, in the distillation process, an analyzer with several probes can monitor different points in the process, generating real-time information on the ethanol content, both anhydrous and hydrated, providing information in real time for process adjustments and corrections, allowing the control room to actuate at the process with better information. That's what I would like to share with you today. It's a brief introduction of the opportunities for NIR inside the sugar and bioethanol industry, so you can evaluate what fits better for your company. We understand that the use of online analyzers is a very current topic with great potential in industrial automation and 4.0 industry. And the message I would like to leave you today is that you can count on the experiences of Bruker and Solar Datalab for the development of the new projects in this area. Unfortunately, due to unmatching agendas, this presentation was recorded previously. But for those who want to discuss any specific application, Nicholas will be pleased to collect your doubts so the detailed information can be discussed later. Once again, I would like to thank Nicholas for this invitation and for everyone's attention.